hope I haven't scared people too much with groupoid speech. The advantage is that today what I'm going to talk about are manifold versions. So I've done a little bit of sort of redacting on the text that I want to go to. So the reason I'm going to start with Siebert is that on some sort of large picture conceptual sort of level, that's exactly what you want to do. So it's the obvious first easy idea. Well, it's not easy, but it's that, that would be the right thing if it worked. It's also, it's not clear that it worked. That paper isn't published. And so it's a little more kosher for me to go through it and say what I don't understand. But I also figured that before I complain about other people's work, I should show my own mistakes. So not only are mistakes humans, also stupid mistakes are human and they get published. So this is, pretty important, basic paper about the quilted flow homology. And of course the mistake is always in the regularity. So at some point we prove that there's, a space of regular J's so that, some moduli space is a smooth manifold. Well, great, let's see how we do that. And don't worry, there's not going to be a South-Snell theorem. So we want to find our regular J's and we note something. Namely, we note that the unique continuation theorem applies to the interior of every non-constant strip. So the situation is that we have several strips. Let's say we have two. So there are two strips, and whenever a single strip is non-constant, I have a unique continuation theorem and I can do something. So this argument here works then if all my strips are non-constant. Great. And then we're done because we just, in parentheses, remark that constant solutions are automatically transverse. So we've covered two cases here. All strips are constant, or no strip is constant. That finishes the proof exactly if there's one strip. Which of course is the old situation in Floer theory, which is why we didn't think of thinking about the case where one of our strips is constant and the other one is non-constant. But stupid mistake. Hard to find. We spent a semester fixing it. After people had asked us about this several times, and we'd always sort of you explain something and they go away thinking, oh, I just didn't understand them. So it took me a while to understand that there was a problem. So not all sets of cows are either all pink or none of them are pink. With that being said, anything that we're going to find, if we're going to find mistakes, it's going to be less stupid than that. So I just thought, it's good for you guys to actually see writing on this. This is the real literature here, and it's not that bad to read, I think. So let's see. Right. So this is a mid-90s paper on, we want to do something in general symplectic manifolds, and by my mantra that means you really have to deal with like bad bubbles. So there will be multiply covered bubbles that you can't make transverse by wiggling with J. So you've got to come up with something else. And the buzzwords just from the table of contents that I see here is some abstract transversality, and the specific buzzword is a localized Euler class on Banach orbifolds, which we're going to turn into Banach manifolds. So let's see what our statement is here. Right, so what do we got? We have a closed symplectic manifold. Great. We're comfortable with that. Then there is a slightly weird thing we need to figure out. What is the space of stable parameterized marked complex curves in M? Oh, of some Sobolev class. And then there's an assertion that we should understand, so that's supposed to be a Banach manifold. And then we'd like to have a bundle over that space. Some fibers being LP spaces. And what else? More words. An oriented Kuranishi section, which, is the D-bar operator. So that all seems good. And then the zero locus is the holomorphic curves. So the one thing that is not entirely clear to me at this point is whether he's quotienting out by automorphisms or not. Is this modular reparameterization or not? But let's see. So, and then there's an assertion about it that says this is a locally finite dimensional Hausdorff space with compact components. Compact I like to hear. The finite dimensional Hausdorff, I think, refers to some Hausdorff dimension here. So let me not underline that. Let's say it's a Hausdorff space. So it's supposed to be compact, so we had better quote it out by reparameterization here. Which then raises the question of what do we mean by L1P or W1P here. What else? We have some Deligne-Mumford space of underlying algebraic curves, and we are going to restrict ourselves to this case where that Deligne-Mumford space is just the point, because we want to work in our test case. Basic example. We were looking at spheres, so genus is 0, and we had one marked point. So that gives us 1 here. So those are not stable domains. Right, so we'd usually fix infinity, just that one marked point in the sphere. So then what? Then the claim here is that there is a, let me also maybe make that one. Upshot is that there is a localized Euler class that seems to be a homology class in this moduli space of holomorphic curves. And then in our case, there's a silly situation where you map the Gromov-Witten map then takes tensor products of homology classes in my symplectic manifold and maps to the homology of the point. Which should be something like our base field, maybe Q. So this is what we're expecting to be sort of the curve count as you're going. This asks these K-marked points to go through these sort of K submanifolds. Say this is maybe Poincare dual stuff. Maybe not curve C. And then submanifolds, we call them S. marked points C1 up to Ck, and we're asking them to hit those submanifolds. Right? So this is sort of the fuzzy background that we talked about before. The sort of rigorous statement here is that there is an actual homology class in this total, possibly very singular moduli space. So this is one of the cases where we should sort of expect this Gromov-Witten thing here is what I would have called the fundamental class of my compactified moduli space, and we're seeing something that says it's a homology class. Questions about this statement?
Can you elaborate on the definition of stable?
Yes. Let's see. There we go. So this is in fact the whole sort of background here. So let's see. This so this is this weird, a bit of a weird sort of notion for me, sort of talking about a parameterized complex curve. So that's a tuple CX5. Let me make notes of what we mean in our basic example. In the basic example, the complex base is always just P1. And this X is always just the one marked point. And then phi here is a map from P1 to, right, X here is now my symplectic manifold, so let me call that temporarily M here. So far so good. In this world here, we just want to sort of think about continuous maps. You know? Then there's a notion of morphism between two such maps, which is exactly reparametrizing by a holomorphic map on P1. These guys were, right, so there's that condition. So psi has to fix the marked point. So that's our morphisms. And then, well, before you want to talk about isomorphism classes, that's where the definition of stable comes. Right? And that says, well, okay, so the map on every unstable component is non-constant. So in our case, there's maps that can be stable and there's domains that can be stable. So here the domain is unstable. So the definition of a domain being, well, stable is that it only has a finite set of morphism or self-morphisms. And unstable is exactly saying that this is not just discrete or not finite. In our case, this is a four-dimensional group. So if I added one more marked point, it would be two-dimensional. If I add yet another marked point, it becomes zero-dimensional. And in fact, the only map from the sphere to itself that fixes that fixes three marked points instead of permutes them is the identity. So it's not just a finite set then, but the identity just. And so that's a stable domain. This weird inequality comes from, right, there's this 2 genus plus k, right? So in my case, genus was 0, so I wanted 3 marked points to get things stable. If I have a torus, so then genus is 1 here, I need 1 marked point to sort of fix the automorphism group a little. Because if I don't have a marked point, I can rotate the torus. And once I have higher genus, the higher genus surfaces don't have sort of continuous family of automorphisms. Does that clarify? So that's So not only do we have these extra symmetries, we also can't somehow vary the complex structure on our underlying domains. So that would be silly. All the complex structures on P1 are equivalent again to the standard complex structure. So only that one choice. Well, you could take all the choices, make this humongous space of complex curves, but then you have to quotient out by a lot more. So what happens here is that we sort of take a canonical representative of that to Lin-Manfred space. Right, so that's stability of the domain, but now we need to talk about stable curves or stable maps. So, where's that happening? And then there's some talk about L1P or W1P. So, first, right, so a map now is stable, right? If, so the domain in general can be a nodal domain. So this curve here can be like a bunch of spheres, some nice tree of spheres. And then whenever the sphere has two little marked points so that it's unstable, we're asking the map on it to be non-constant. So that something interesting happens. Reason for that is that then, when you then look at the isomorphism classes of this space of continuous maps modulo these reparameterizations, it is a pretty brutal quotient, but you never have more than sort of a finite fixed, you do have fixed points under sort of, some group of isomorphisms, but your isomorphisms in these automorphisms are always finite. So
if you have locally injected, then it's stable at its element.
Then indeed, right. So let's see. So the stable here has something to do with Hong from phi to phi itself, right? Which is the psi's that fix phi. This being finite. It's just not, it's not said. There's sort of this is easier to check, right? That maps are non-constant someplace. This is the important, implication of that. So let's see. So that's the C of X. Right, so let me write that. In our example, it's C0 maps from P1 to X mod reparameterizations. So then we're adding something about about things of class L1P, which is just another way of writing Sobolev space W1P, and those are now supposed to be isomorphism classes of continuous things, which are in particular W1P. So this is really just W1P maps, also mod out. So I think that's just a typo, and here's another way of talking about being non-constant. You'd like the area to actually be positive. We can talk about this now because we're W1P, so you can sort of integrate d phi. And eventually we know that non-constant holomorphic curves have positive area, so it makes sense to throw all the others out. So, good. Yeah, I did claim at some point that that is a somewhat problematic space because we're quotienting by something that acts nowhere differentiably. So we'll be very wary of assertions about that space. And then, right, from this cutout, we should find the actual pseudoholomorphic curves. Right? So those are the ones that, now he's talking about every irreducible component. We only have one component, P1. So we're asking this map from P1 to M to be a morphism of almost complex manifolds, which is to say it intertwines the complex structures. So that's exactly the d bar operator being 0. So here's your in our case compactified moduli space because we're assuming that there's no bubbling, and that now sits in this quotient space of W1P maps. So that's our basic setup here. Let's see. So now, and then there's again, so there's a bunch of claims about things being, so this quotient space now here is claimed to be a Banach orbifold, so that better not be a differentiable Banach manifold as we would think about it, because that would mean transition maps need to be smooth, which we kind of convinced ourselves won't really happen. So there's going to be a weaker notion of Banach orbifold, so then we're going to need some notion of bundle and section, and then understand how we get that fundamental class. So, right, guiding questions here, right? Exactly on, so we're on sort of this case. Claim as there was an Euler class of something, and you saw M bar was written as section, as 0 set of this Kuronishi section. So, exactly what, in this case, what is the abstract form of S? So that means what is meant by Banach manifold or orbifold, and what is meant by Kuronishi section. And then why do we have an Euler class, right? Or what is that Euler class? Right? And then the other sort of complex of question is how does this actually apply to, for example, our base space? How do we get this structure? Well, let's see. So the graying out has to do with the fact that I don't want to worry about isotropy. So this is all orbifold speech here. So, right, so when we're talking about Banach manifold here on a Hausdorff space X, what we should have in mind is X being this CMP, which is this quotient space of maps. P1 mod reparameterizations. So this is a little hard to pass here. So we want a fine covering and a functor to some category where there are some open embeddings. So first of all, let's see. A covering, I can just about guess what that is. So I want a union of some open sets. So, and we're turning that into a category here by calling each of these UIs so each open set by itself is an object. This is different from what we did in the groupoid world, where every point in this was an object. For X is X is not going to be compact, but if X was compact, we could cover it with finitely many objects. And so then we'd like morphisms only if Ui is actually included in Uj. So now you could imagine a cover here where no two sets are included in each other, and then you suddenly have no morphisms at all. And that's not a good situation. What you should think of here is a fine cover that says, in fact, I think what you should assume is that whenever you have two open sets and a point in the intersection, then you should find another one of the open sets that actually lies in this whole intersection. That should be your UK here. So that way you could encode sort of how you glue all these open sets together by all these inclusions into. So then this UK here includes sort of into U1 and into UI and into UJ, and so you have all these morphisms. So hopefully you could keep track of that. But it's going to get less crazy in a moment. So let's say we have a nice fine covering here. And now we want a functor. Holy smokes. So to local uniformizing systems. The good news is that those got a lot easier when I forgot about the isotropy action. So let's see. So that is now a category whose objects simply are open subsets in a Banach space, which apparently is fixed here. So, and having a functor now from this category to this LUS means I should think of UI as sitting as an open set in my Banach space T. That looks more like the beginning of a Banach manifold. And I forgot to copy that, so I copied it out by hand. So morphisms in this category now are continuous maps between open sets and Banach spaces. So I'm going to identify each of these UIs with an UI hat that's an open set in my Banach space. And then this morphism here tells me that I should have a continuous map between the corresponding open sets in my Banach space.
Now this continuous map doesn't really look like an inclusion necessarily.
Right. Because you could, those two look like balls. You could model them both like, the unit ball, right? So then you just have to have some way of talking about the transition map. But that should certainly be a continuous map. And the good news is that the claim here is that also that each HOM, so each of these inclusion maps that becomes a continuous map actually needs to be an open embedding. So in this case, it would be taking this little circle and embedding it into the bigger green things, factored through these embeddings into the Banach space. So that is pretty much, if you forget about Banach spaces here and think about Rn, you can sort of convince yourself that this is the definition of a topological manifold. So this is the definition of a topological Banach manifold, I would say. Right? And so I think with that we're sort of fairly happy. We actually did construct these local slices for this space, that were open sets and Banach spaces. And we did have these sort of transition maps that I claimed they were non-differentiable, but for us they were something of the form V goes to V composed with array parameterization, and you could try to check that that's in fact continuous in whatever slices we have there. So that's the claim here when we're saying that that's a Banach manifold. So nothing bad happened yet. Good. And then of course, this is the base, and really what we want is what we, is a bundle over our space. And a section, which we essentially like to be the d-bar operator, and we need to give that some decent structure. So we need to talk about how this E here is in fact a Banach bundle. What do we have? This projection here needs to be surjective as the level of topological spaces. And then all these functors here. So these the covering of open sets here becomes a covering, by taking the whole pre-image under this projection. And then we would like, within the sort of local uniformizing system, the sort of open subsets in a Banach manifold should in fact be the open subsets of this cover of the base times a fixed Banach space. So, this is key here that looks very much like a bundle. Again, all transition maps and all the structure just sort of continuous here. And in that world, we can also very simply talk about a section, That's just now something that, with this projection here, composes to the identity on the base. So, if that was all true in the smooth category, for a space of parameterized, unparameterized maps in the d-bar operator, then we'd be very close to just having a smooth Fredholm section in a Banach bundle, and we could run transversality, or we could run our finite dimensional regularization theorem, as a theorem for Fredholm operators, right? But we're notably going to be missing differentiable structure, and so that's where the interesting piece of the sort of setup comes here. So, and I've tried to decode what happens later in the paper, so edited a little bit more out here. So this is the beginning of the answer to what actually is the abstract form of our section. So again, what we're thinking is the section being the d-bar operator on W and P maps mod parameterization. So there is a notion of a Fredholm section relative to something. So the relative to something is another submersion of Banach orbit folds from our base space to S. However, I believe that S is later on the Dillon-Mumford space, which in our test case is simply the point. And there is only one submersion from this space to the point, so I can forget about that structure. So S is not going to have any interesting structure, and P just takes the entire set X and maps it to the point. So I'm going to forget about that. So then I'm just talking about a Fredholm structure. Right, for this. Right, so we already have orbits, I mean manifold structures, Banach manifold structures, and Banach bundle structure. So what the claim is that in the local trivializations of my bundle centered at a zero, the idea is that the base splits into, a product of two open sets, where this L piece here is finite dimensional. V then obviously has to be a Banach space of open set in a Banach space. And if we now look at the section in this splitting, the claim is that it is differentiable only in the direction of V. So the linearized operator here only takes the tangent space to V. So this is a little, right, there's D sub V here. Capital pi is the trivialization. That's this guy here. So, right, so we're getting a family, at every point L comma V, we're getting a differential just in V direction. So, D. Simplify this at a point L V of S. Well, this D here is now sort of just mapping from tangent space of V to the fiber of my bundle. So that is hopefully sort of believable, at least in the gluing theorem. The thing that was not differentiable was the shift by the gluing parameter. And so I know we're not in the gluing setting here, but in gluing, I think what you should think is that L is the sort of gluing parameter. And there's only finitely many of them, so that's your finite dimensional space, in which you lose differentiability. So then, if you go through the gluing theorem, you actually do have derivatives, with fixed gluing parameter. So that's fine there. In our case, we'll have to ask ourselves at some point, how do you get this splitting when you look at the local charts, in our quotient space here. So, right, but note, so what he's not actually saying is, so he gives these local trivializations these forms, right? So locally. This should look like L times V. But he's not saying that these need to be compatible in any sense. And so in every local chart you have some directions in which your section is not that differentiable, but these directions don't need to match, with the next chart. So that's good news. And right, yeah. So we talked a lot about differentiability, and then of course what you really want to say also is that definition of Fredholm means that this derivative is Fredholm. So I just forgot a part of my domain. Why does this Fredholmness condition still make sense? Yeah. Well, yeah. If the whole operator, including derivatives in L direction, was Fredholm, then it would, that's only a difference of finite dimensions here. So, the actual Fredholm index that I should think of here is the Fredholm index of this here plus K. So. That's why it's important that the directions in which you lose differentiability is just finite. So that way, talking about Fredholmness makes sense. So this is like saying I have some local slices in which the d-bar operator is Fredholm. Yeah. Fine, we probably believe that. And so now, what is our Kuranishi structure for the d-bar operator? So history has kind of overtaken this notion here. I would nowadays not call this a Kuranishi structure, but maybe a global stabilization. But what is this? Right? So we have the same situation. We have now a Fredholm section in our bundle, and a Kuranishi structure is a morphism. That's a typo here, I believe, from a finite rank bundle over an open subset of X. So that's our X prime includes openly into X, this was a W1P space. So F is supposed to sit over this. And we'd like it to be finite rank. And, well, so, okay, morphism. So that says it's not necessarily injective on the fibers. And what else? So this subset X prime here should contain the zero set. Right, so this S here, this contains the zero set. So X prime should also contain the zero set. Yeah. Which is our compactified moduli space. So far so good. And, well, so now, how does that stabilize your section? Well, stabilization is a notion for Fredholm operators. So we're going to go into local charts like the ones that we have from this Fredholm structure. And there, so again, just at the zeros, we're asking ourselves whether the Fredholm operator gets its co-kernel spanned by, whatever this is here, that's our tau. So the fibers of this finite rank bundle over every zero in here should, cover the co-kernel. That's what I call the stabilization before. And, well, there's just, a condition on this stabilization, within every chart is that, this should be a differentiable, bundle map, which makes sense because that, stabilizes a differential equation that you want to solve. Apply implicit functions down to. But again, there's always just sort of a local differentiability here. All right. Good. So that's our ideas here. And then, of course, you have to somehow, right, there's always going to be the problem, well, if you have two different choices of Kuranishi structures, is that going to give us, the same Euler class in the end? And so there's a notion of compatibility, which is really nice here. It just says if you take sort of these two bundles, well, they're going to sit over x prime and x double prime, but their intersection is going to cover the zero set also. And you should be able to sort of sum them and map into here. And that's supposed to be a Kuranishi structure also. Why is that ever a problem? First thought would be it could be a problem that, if you asked this bundle here to actually be injective on the fibers, if you asked F to be a subbundle of E, you can't necessarily sum two subbundles and get a subbundle. You might have to perturb them so that they're transverse. Because otherwise, if they sort of have collinear vector on some fiber and then on another fiber become transverse, then sort of your dimension jumps. You don't want that. But we're not asking for injective fibers. We're not asking for a subbundle here. We're just asking for a map. And so it's certainly a continuous map. The reason it's a condition is that the Kuranishi structure here wants to be differentiable. And that, for f and f prime is possibly with respect to different nice local trivializations. So this is something to do with the sort of Fredholm structure, even here where we're locally identifying this with this product and have differentiability in all but finitely many directions. So somehow those local shards for these two stabilizations need to fit together nicely. But this is probably the easiest equivalence notion you'll ever see. That's why. It's not really important for what's coming next, but I just wanted to show you a case where compatibility is actually not so bad. So, right. That's a whole lot of neat structure here. The question is, well, one, how do we get it in our example? And two, once we have it, how do we get an Euler class? So, I think the Euler class here, well, that's a little bit of an exercise. So if somebody wants to check that, that would be neat. But that sounds very believable. So, this is a little bit preparation here before we make the Euler class. You need to think about what you mean by transverse now, right? When you also always just have this sort of partial differentiability. So, what do we mean? Goodness, this P here, oh yeah, forget about that P. So, we just have a Fredholm section of a bundle, and there's a subset of the zero set at which we're saying it's transverse if in the local trivializations the sigma is surjective. So that's the sort of the local trivialization we said that, right, so we looked at this product, and sigma is the d in the direction of b of my d bar operator. So that's what I would like to be surjective. The direction of b, s. Right, so this is that sigma. So that's a little bit stronger than what we maybe got out of like getting a regular J, right? Because we might have had to split off some finite directions, to sort of get differentiability. And even after the splitting, we want that operator to be surjective. It's not unlikely that that could be done. In any case, we're going to, not apply this to the d-bar operator in a moment, but to a stabilized section. So really, what we are going to do is take, what is that? F times E. Is that right? Oh, F sits over X prime, right? So my section is going to be the map from this stabilization bundle to E, right? Which, remember, so we're sitting over some subset of maps. So at every equivalence class, I'm now allowed some finite dimensional extra things here. And what I can do is I can write my d-bar operator, hopefully make sense on these equivalence classes, and I can add this f. Let me just say little f. Well, there was the tau was this map from f into here. So this is something like tau plus d bar. And this being a stabilization means exactly that this section will, that's the one that will be transposed. This is what we want to apply this to. And then, so now, right, so this is, again, a section over a Banach bundle, except now F is the whole Banach bundle, that locally, F looks like, a splitting of the base, L times V, and then, just a finite dimensional vector space. So these two are finite dimensional. But we might, so we have differentiability in everything other than L. So now you can ask yourself how to apply an implicit function theorem. Well, you can apply it whenever you just fix a slice. You fix a point in L and just sort of look in these directions, and that's where nicely we actually asking for the derivatives in those directions to be surjective by themselves. So in every slice you can run an implicit function theorem and cut out something with a C1 map. So it should be a C1 manifold, right? Except then as I vary L, those derivatives were supposed to vary continuously, I guess. That's where the reminder comes in, right? So these are the derivatives, and we wanted them continuous at 0. So since these are derivatives on infinite dimensional spaces, there's a little bit of a dicey question of continuous in what topology. And I believe you need the operator topology. So actually, this is bad. Linear maps from, I guess, B times F0 to the fiber here, E0. Certainly, if you take that as the definition here, that should be just a sort of little bit of an exercise to check that what you're getting out, when you sort of glue all these slices together of this sort of continuously varying section, is you're actually going to get a topological manifold, which will be finite dimensional because the thing was sort of a Fredholm operator before, and you just added finite dimensions. So, and in some sense, this is what we looked at before. This is sort of the use for which d bar U is in this extra fiber that we allowed ourselves. That's so that's right. So that's this proposition. We're claiming that this is a topological orbifold now, topological manifold. And then what? So, see? Then we actually make our Euler class with that. So same setting as before. Yeah, we have a Kuranishi section is a section together with F. So we now have this E over quotient map S, which is the D bar, and we also have this stabilization that covers the co-kernels. So we want to get a, I don't know in what sense that, I think it's localized in the sense of this vibration over the Deligne-Mumford space, which we don't have because there's no Deligne-Mumford space in our example. So for us, this is really a Euler class, which is now supposed to lie, let's see, D plus B, that I think is exactly the right thing. So D is the Fredholm index of these derivatives in just V direction of the D bar operator, and L I think should be dimension B in this case. And Z here is my zero set. So that's my moduli space. So, well, yeah, this is a sort of an axiomatic definition here that says, well, you know, it's the right Euler class if it has this property that if my D bar operator was transverse by itself already, you know, so if my zero set already was a topological manifold of the right dimension, you know, then the Euler class should be exactly its fundamental class. That's the reality check. And how do we get it? Right? That's exactly this stabilization construction here, where, right, so I wrote before sort of S, I wrote D bar plus tau as the stabilized action, and that was a little, you know, fuzzy because really, what do we have here? F sits over X prime, and yeah, the map tau is defined on this fiber, and then the map D bar is just defined on the base here. So that's why there needs to be that projection in between. So with that, I pull the D bar up to the fiber, and I can sum them. So this section is transverse. Right. This is what we looked at before. So this nice zero set is now a topological manifold. Let's be a little bit careful though what that is. So this Z twiddle is now, well, let me write pairs of base points and elements in the fiber. And what I want is D bar U to be equal to that tau of F. You can almost identify this with the space of U's whose D bar sits in the fiber F. You can only almost identify it because the tau might not be injective. So the neat thing with this space is that you don't have to worry about tau being injective or having a tau inverse, because so this space now has a nice section that that's the tautological section. This is the one that takes this pair to just F. And so that's this. Yeah. Nice stabilization construction, except this time it's global. Right, so if we now look at the zero set of this canonical section, it's going to be exactly the point C twiddle in this, where F is 0, so that's exactly the holomorphic curves. So we've hence described, our compactified moduli space here as the zero set of a section in a finite rank bundle over a finite dimensional topological manifold. So this is a global finite dimensional reduction. And now, if you now wanted to construct the Euler class of this finite dimensional reduction, sort of by a perturbation and implicit function theorem, then you would need some more differentiable structure. But Euler classes are defined for topological bundles, so which I'm certainly not qualified to speak about, but trust the algebraic topologist to say that. And that's exactly, I think, the definition of the Euler class here, right? So, right, the M bar here gets identified with the zero set of this canonical section, and we have the M bar exhibited as the zero locus of a finite rank OB bundle over a finite dimensional orbifold, and these things have Euler class. Oops. So, which sits in the zero set, or which you can make sit in the zero set, which we've identified with our compactified modular space. So, on the abstract level, that's a pretty easy story. You just had to, so, essentially we sort of did the sort of dream proof of, let me just assume that, maps modular reparametrization is a Banach manifold, and that I have a Fredholm section, then you did this global stabilization, made this global finite dimensional reduction out of it, get the Euler class. The only thing is that we needed to somehow worry about not lack of differentiability. So there's a little bit extra structure there. So I think on that level this is pretty easily checkable and very convincing. So that means the one thing that I'm then dubious about is, well, this other question, how do we actually get this structure? So how do I get all these nice, like, local uniformizations in which I have differentiability only in finite, in everything but finitely many directions? So let's at least see a little bit of the language. So certainly this is the theorem that you need to look for, right? So this space, that was our base space. So let's write this out again. So this actually, we're looking at W1P maps from the sphere to our symplectic manifolds modulo reparametrization. access infinity of Möbius transformations. So we're claiming that this has locally the structure of a Banach manifold. Right? Let's say I know that all of these are injective. So then I also don't have to worry about groups here. Right, so if A is somehow a very primitive class, so let me assume all of these are injective. Well, right, so for that we should also, right, oh yes, and we also want a Fredholm structure at the same time. So that means we need these charts. And somehow these charts are now S times V hat. So these local uniformizing systems at, this is at a map, are supposed to be, so let's see, locally, claim is that this is locally, looks like S times W1P of P1. Phi is my V here. And the S, however, lies in the tangent space to the Deligne-Mumford space. So S becomes a point. So no extra S direction here. So good, but not all hope is lost. There actually is, a discussion of the case when the basis is unstable. And so there the idea is to take something called a rigidifying slice. So I believe what's happening here is that this here is capital V, and this V hat that we're taking in there is something that we're getting from local hypersurface conditions. So this would be something like the sections that you could add to V, right? For which at two fixed points, say 0 and 1, right, I stay in my hypersurface, so I have to stay in the tangent space. So what's happening here, right? So V at 0 is an H0, V at 1 is an H1. And locally we identify this quotient space here with all the maps near V that also at the same points go through the same hypersurfaces. Right? So then that's a local model for this, via, so this I can map to this quotient space by taking X V of Xi and then quotienting by reparametrization. So, the claim was that that's actually a local homeo. So this is what I would call a rigidifying slice. And then let's see what's happening with that. So, because what we should think about now is, I think there's some question here about change of coordinates, right? And that's the first place that really puzzled me. So a whole lot of things going on here. So there is a, right, so C prime or phi prime now is a map close to the base one here, so maybe that was V here, and now I should think about it. V prime. I should think how that, the local uniformizing system, or this sort of nice chart there, is compatible. So, a whole lot of, well, my one component is unstable, and there's, right, so there's just the question of, right, what the transition map is. And that's exactly the composition with the quotient map. So S doesn't exist now. So let's see, so this is the V hat. And I might have a V hat prime here from different hypersurfaces. And the quotient map is through the W1P mod automorphisms. Those are two local homeos. They have some overlap, and there is a composition here which is claimed to have this form. So what was, not sure what pi is, but what I find puzzling is that V seems to just be, undo the exponential maps. What I'm missing is a reparametrization. So something that, what do we have here? So I'm thinking here of xc that goes to x v of xc, which is equal to x v prime of xc prime that came from xc prime here. And this here seems to come from assuming that there is no reparametrization happening between the two. So, but yeah, that would be very special slices. That's all not, the end of the world, because the claim was actually not that we do have differentiability of the transition maps between the different shards. So really all we claimed was that we just wanted Fredholm structures at every point. Right? So we just wanted these things locally. We didn't ask for them to be compatible with different, trivializations. And what we did convince ourselves of at some point was that if I restrict my d-bar operator now to V, that's even without an L, right? So my V was just this W1P. Well, it was a finite part of W1P maps in a pullback bundle. So it was like C's that had these hypersurface conditions. I can restrict my d-bar operator to that, and that will be Fredholm. Yeah, we know that. And so once that's Fredholm, we also know that we have, at least locally, all these stabilizations. So that's all fine here. That's okay. And how do I get my stabilizations now? So let's see. So claim is right. So I have I can certainly cover this by finitely many, oh no, not by finitely many, but by images of these charts here. So, so locally, it looks like this. Oh boy, sorry. Let me give this some name here. So those are the local slices. V hat, maybe I. Right, so there's some different hypersurfaces, different centers. So some union of this V hat. I's, right? C bar on each V hat I is Fredholm. And that means I can find locally finite rank, even subbundles over these V hat I's that as a subset of these will cover the co-kernel. That's all locally. The idea is, well, let me multiply this with a cutoff function. So this is tau. Let me multiply this by a cutoff function. Psi. That way I can extend it maybe to my whole space. But each one then just still only covers the co-kernel locally over something that's maybe even smaller than that V hat. Still, all I care about is covering the zero set. Right? So I'll cover that by finitely many now of these domains where this stabilization actually does stabilize. And then I can make a big stabilization simply from taking the product of all these Fi, which now all sit over just a neighborhood of this zero set that gets covered by these V hat I's. So this. Oh, that's out. So, right. So at every point in this neighborhood, one of the Fi's covers the co-kernel, and so if I take the whole sum, that's going to cover the co-kernel. Yeah. And the beauty here is that particularly the beauty is that I do not care about injectivity. So there is this whole notion of sort of obstruction bundle, that would have to sit in here and actually be a bundle. Right? So in order to construct that, you would need all these sums here to be, injective. And that's not so easy to get at. But the sort of stabilization all seems sort of fairly easy to achieve. So that may or may not be the full story in our basic example. And so then you can go and ask yourself whether that still works when you have gluing. When you get a nodal map, what is your topological Banach manifold that all the continuous maps and continuous nodal maps sit in? So that's something that I haven't tried to decipher. Well, I've tried and I've failed. So I think well, one of the places where I'm suspicious is in this definition of the differentiability, which is exactly here, and there was this question of, these differentials need to be continuous in what topology, and that operator topology, at least to my knowledge, when you do gluing, is not good. So you might not have continuous differentials there. Certainly, when I tried to do it in the polyfold setup, I didn't get my differentials to be continuous. So, yeah, that would be one place to look for fun in that paper. But, yeah. Mainly, I think it's sort of the right sort of first abstract regularization approach, because it does not go off into groupoid language. So we have one probable construction of a fundamental class that we can at least use as sort of a base case to compare others to.